Hi, today I will be solving the previous problem where there is a closed system of air and water and you are given certain values such as initial pressure, final pressure, initial temperature, the amount of water in the system, and you will need to find the final temperature and the total volume. And we will be doing this today in Python. So first up here in this first line, we are grabbing our data from a GitHub website. Well, not really our data, but rather our library of tools. And this is done by grabbing the path to the chi module imports, which is seen down here. We also need to import a dot map structure, the pandas for our data frames, and then the tools to help computate our total volume and final temperature. And so right here we have our variable, just call it p, is equal to our library of chi and then dot props. And each of these have certain data within this chi library. And so this is for the components of air, which are nitrogen, oxygen, and argon, and then also water, which is in the system as well. And so first what we need to do is make a dot map structure. So then we'll make our dot map structure of just C, because that will be used later on in our model. So C equals, we'll say, dot map, and then we'll move down. And so in this dot map, we'll put in our initial and given values. And so what we have are total water to begin with in the system, which is a kilogram. So we'll do C dot W underscore total for total water equals 1. And this is kilograms. And then we will then do our initial pressure, which is C dot P underscore I. And this is equal to 1 bar, which is 100,000 pascals. So we'll do 185. And then we'll do the same thing for our final pressure, which is 2 bar, which is 200,000 pascals. Then after this, we will then put in our initial temperature, which is room temperature at 298 Kelvin. So that is C dot temperature underscore initial equals 298, and this is in Kelvin. And then after this, we also have our moles of water in the vapor phase, which is desired, which is 0.3. So then we will do C dot moles of water, so we'll do NW vapor phase, and this is desired, so we'll then put underscore D equals 0.3. And then after this, we then will calculate our volume of water initially in the container from our mass of the water, which is 1 kilogram. And we will do this by dividing the mass divided by the density of the initial of the water at initial temperature, which will be C dot volume of water initial equals the total water, which is right here. So just copy and paste that, divided by, then we will grab from our chi library, so that'll be the density, make sure that I run these first. So now that those are working, I can then move on to row L, which is density, and our temperature, which is asked as the argument, will be our temperature right here, which is 298, so we'll do C dot Ti, and instead of putting in 298, we put in the C dot Ti for our initial temperature in case we then change that value later on. And we want this of water, not nitrogen, oxygen, or argon, so we'll put the last index, which is 3. And so then we will calculate, space that out, we will calculate the, we will then do a range for the final temperature, which will be calculated in our VSC. So we'll do C dot T for final temperature equals, and then we'll do range, which is part of our library up here, as you can see. So this basically will take guesses and educated guesses and plug them into the VSC, which will then be used to help calculate our unknowns, which are total volume and final temperature. And so for this, we will have, we'll say, there's somewhere around 350, and then the low, which needs to be higher than our initial, say 299, and then high, which we'll do as 500. And then we need to do the same thing for the other unknown, which is our total volume. So that will be C dot V underscore total. And this will equal the range. And then the first thing we'll put is, we'll say 0.015 cubic meters. And then the low will be 0.001 cubic meter, and then the high will be 0.04. So then from there, we will then go on and we will make a model, and we will just call this model. So the arguments are C and R being our intermediate values. And what we need to put in this are equations that are necessary to help solve for the unknowns in the VSC. And so what needs to be put in will be our partial pressure of water, which we'll just call PW, equals, from our chi tools, P dot PVAP of the final temperature, which we'll find. And so we also need to make sure that we index this correctly so we don't get multiple values. And after that, we need to calculate our volume of the vapor phase, which will be R dot V underscore VAP is equal to the total volume, which will be C dot V underscore total minus the initial volume of water in the liquid phase, which is C dot VW underscore I. And then from there, we will then calculate the moles of air in the system, which will do air underscore N is equal to, and basically what you're doing for all of these are either ideal gas law or just manipulating basic equations such as the total volume being the water plus whatever the air is. And so for this one, we'll take the initial pressure, C dot, which is given earlier, and then this will be multiplied by the volume of the vapor phase, which is up here. And then this whole thing is then divided by the gas constant R times the initial temperature. And after that, we need to calculate the moles of water in the vapor phase, which will be R dot, and this will be useful for our tuple later, R dot we'll say moles of water vapor phase. And this is equal to the partial pressure of the water times the volume of the vapor phase. And then this was divided by the gas constant times the final temperature. C dot T. And then we also need to calculate the pressure. This is the final pressure. And this is the moles of air, which is underscore N, times the gas constant R, times the final temperature, divided by the volume of the vapor phase. And this whole thing is added to the partial pressure of the water. To make that clear, we'll then separate this with parentheses. And so now that we have this, we can make our constraints. So we will do pressure constraint is equal to, we will have our final pressure first, which is C dot P underscore F. So basically, once this pressure calculated here equals this, it'll output our answer. And it'll do the same thing for the moles of water in the vapor phase. So we'll do the same thing. So we'll do moles of water constraint equals, just copy that down. So then once the calculated number of moles of water in the vapor phase equals the desired, it will then stop and output our answer, which is this right here. So now we want to return these values. So we'll do this. All right, and now we want to calculate our VSC, which will be right here. So VSC. And then we'll put in C and model for that. And then we also want to solve it. So we do VSC dot solve. And then so now let's run the whole thing. Oh, we need to run this so our model is defined. Now that this is working, we can then show that our code is running by doing VSC dot V, our data frame of that. So then we can show that. So here we can see that our temperature is 302, which actually seems a little bit off, so we might have to go back and change, make sure all our values are right. So after going back and looking at the code to see what might have been the problem, I started doing a number of things like making sure these are floating points, checking the ranges, making sure everything was entered in correctly. And what I found was the problem was that I was missing certain parentheses. So there weren't parentheses right here, which would make this quantity divided by that, then times that, rather than this quantity divided by this whole quantity. So that then changed the total volume of my container to be much lower than what it should have been. And so now when I run it, I'll just run all and show you that now I get the volume and final temperature that I want. Thank you for watching.